Myself Jayeeta Majumder, Assistant Professor of Department of Computer Science and Engineering of Haldia Institute of Technology. Today, my lecture topic is cache mapping technique. So, before mapping techniques, first I discuss what is cache memory. So, from the memory hierarchy, we know there are the hierarchy structure at the lower level. If we consider from bottom to top approach, the bottom at the bottom is the secondary memory, then the primary memory, then cache memory, and finally the register at the top. So cache memory actually we consider it is a part of some primary memory, and it is a fast memory which is fabricated in the CPU chip, and it comprises with the transistors, so that's why it is too much costly. So minimum less amount of cache memory is used in our system. And if we consider the access time, so the access time of the minimum compared to all other the memory structure. And next is why we use the cache memory in our system. So if our target is to execute some program, and the program is consist of nothing but some variables and some loops. If we consider the loop variable which is frequently used in our system, so suppose I write some code, suppose I equals to 0, I less than 5, I plus plus. So and within this, so suppose I is used, suppose a equals to a plus I. If I consider this small section of code, so I is the loop variable whose starting initial value is 0, and it incremented by I plus plus, that means I plus 1, and up to 5, that is 0, 1, 2, 3, 4. So these 5 values actually passes through this loop, and inside the loop the statement is a equals to a plus I. So that is the nothing but it is the a is added with the I values. So here I is the loop variable, and this particular loop variable, it is a variable obviously stored in memory in any of the memory of our system. So during execution, if we every time we access the primary memory to access this loop variable I, so it is time consuming because main memory speed is very much smaller. So to increase the access time or to increase the throughput of our system, if we place this I variable in the cache memory, then easily we can access the data in the cache, and from the cache we actually access this and the I value is calculated. Why this concept comes? This concept comes because if we consider this is a CPU and this is our primary memory, that is the main memory, and the CPU actually placed between cache memory is placed between CPU and the main memory. So if we store that loop variable within the cache memory, then CPU initially first search out the cache memory for the data. If it is not found in the cache, then it searches to the main memory. So if the data in the cache memory access time is compared high with respect to other memories, so our access time is increased, along with the throughput also the system throughput is increased. So that's why I written here that is for frequently used data during the execution, we stored that particular loop variable in the cache memory. And next point is cache access time much lower than the main memory access time. That's why cache memory access time is much lower than the main memory, so you can easily access the data and reduce the time. Now come to the main point, that is the cache mapping technique. Cache mapping, for the definition, the cache mapping defines how a block from the main memory is mapped to the cache memory in case of a cache miss. Or cache mapping is a technique by which the content of the main memory are brought into the cache memory. Now what it is written means? Miss, that is the term here I use, that is the cache miss. So what is cache miss first? Cache miss is, if I draw the same diagram, it is the CPU, the execution unit, this is the cache, and finally this is the main memory. Okay, so what is cache miss? Initially, every execution when conduct, CPU at first search the cache memory for the data. So if the data is not in the cache memory, then obviously the data is stored in the main memory. Then this term actually comes, that is the cache miss. Okay, so that's why when it is cache miss, you need the data and it search for the main memory, and then the particular data need for the execution comes from the main memory to the CPU. So when, that is the first line, the cache miss means when the cache miss occurs, the data transfer from the main memory to the cache memory is known as the cache mapping technique, or cache mapping by which the content of the main memory brought in the main CPU. So this is the mapping technique. Now suppose the data is stored in a particular location. Suppose I consider the data stored in 1000 location in the main memory. So the particular data from the 1000 location is not comes to the CPU. Now how it comes? It comes in a block manner, that is some block of memory comes to the CPU. So that's why the following terminology comes out. So first point is the frame. Main memory is divided into equal size partitions called as blocks or frame. That is, suppose your memory size is consists of suppose 100 location, and if I consider each 10 memory allocation consists of a block, so 100 by 10, that is 10 blocks present in your main memory. So in this way, cache memory also divided into some partition having same size. This is also one important term, that is the same size. That is the block size of main memory, that is the equal this size, and this size of cache memory, both are same. So this is known as the line. So for main memory it is known as frame, for cache memory it is known as line, but size of the block is same, that is number of location of main memory and number of location in the cache memory, both are same. And finally, during cache mapping, block of the main memory is simply copied to the cache, and at the beginning the cache is empty. So we consider every time when the execution start, we consider the cache is empty at the beginning and the block of main memory simply copied, not transferred. Okay, data is present here, just some copy, it is comes to the cache. So these are the some terminology associated with the cache mapping. And from the diagram, this is the structure of our cache memory. So cache is placed between processor and the main memory. So processor first search the address from the cache. If it is found that particular location, so then the cache returns the data to the processor. If the data is not found in the cache, then that is the cache miss, then it is go for the main memory and searching for the data, and the data comes out from the main memory. So this is the diagrammatical overview of the cache mapping technique. Now comes the cache mapping techniques classification. So there are three kinds of cache mapping techniques. First one is the direct mapping techniques, then the fully associative mapping techniques. Fully means or full. Okay, full associative mapping technique, sometimes it is declared. And third one is the K-way set associative technique, K, or sometimes it is as a N-way set associative mapping. So these are the classification of cache mapping techniques. So one by one we start. First start with direct mapping. So as per definition, it is that is the direct mapping. Any block number in main memory can be mapped into a particular cache line. So, as the single memory location is not transferred, I need to transfer that particular main memory block which contains that memory location. Now, what it means? It means, consider the diagram. So, main memory consists of some block, that is block 0, 1, 2 in this way, and cache memory have some lines. The size of block and lines both are same. So, suppose during execution, block J is required for execution. Now from block J where it is transferred. So as per definition, main memory can be mapped into a particular cache line. That is, a particular line number is fixed for that particular block. Now how we fix that particular line? The formula to calculate that particular line, it is the cache line number equals to main memory block number modulo of total number of lines in cache. So this is the formula to calculate from where to where, actually from which location of main memory to which location of the cache memory it is transferred. So as per numerical example, suppose consider we take this data. Consider size of the main memory is 2 to the power 16. 2 to the power 16 is equals to 4096. And cache memory has, suppose 2 to the power 7 equals to 128 block, and each block contains 2 to the power 4 equals to 16 memory location. So this is important, that is this 16 actually memory location is fixed here. This is the block size, that is main memory also maintain this 16 memory location. Similarly, cache memory line number also holds this 16 memory location. And size of the, then how to calculate the size of the cache memory? Cache memory is 2 to the power 7 is the total block. Each block consists of 2 to the power 4. So that is 2 to the power 11. It is the size of the cache memory. We consider for our example. So block and frame size is 2 to the power 4 equals to 16. So number of blocks of main memory is 2 to the power 16 divided by 2 to the power 4. That is total block is 2 to the power 12. And cache has 2 to the power 7 lines equals to 128. Now we go for the next slide with the data. Now how to transfer? Now the actual problem comes. Suppose we want to transfer memory location 31 and 49. So suppose I draw the diagram. Suppose this is the main memory. Main memory nothing but some collection of some addresses. So 31, so suppose this is block number 0, block number 1, 0, block number 1, 2, 3. So in this way counting goes on. So that is 31. This is a particular memory location. So first we calculate not a single location is transferred. We first declare that discuss, that is a single location cannot transfer. A block of memory location is transferred from main memory to the cache memory. So that's why the second point, that is to find out the particular block number where that particular 31 is present. So that particular block number now transferred to the cache. So how to calculate? The calculation is 31 location in the memory block number 1. How to calculate? So each location, each block consists of 16 location. So 0 to 15, the first 15, this 16 address stored in block number 0. Then 16 to 31, this 16 address stored in block number 1, because our size is here, this is the contents 2 to the power 4, that is 16 memory location consists in each block. So that's why 31 present in block number 1, and similarly similar calculation 49 also present in block number 3. Now our target is block number 1 and block number 3 we need to transfer from main memory to the cache. So now using the formula cache, how to calculate the cache line number? Cache line number, it is the block number, that is the 1 modulo of 128. This is the number of block present in the cache. So 1 modulo 128 returns 1 and 3 modulo 128 it returns also 3. Now in this way block 1 goes to block 1, block 3 goes to block number 3 of the cache. Now memory block number, suppose you require 131 block number you want to transfer. According to the formula, this 131 modulo of 128 also gives you 3 modulo remainder. So 49 also present in block number 3, line number 3, and 139 also returns line number 3. Now how to store or how to differentiate between these two? That is the solution. So in direct mapping, what happens? Total, suppose as per this example, 4096 is the total location divided by 128. 2 to the power 5 number of memory block mapped into a single cache line. So to distinguish 2 to the power 5 different main memory location, we need at least 5 bits. 2 to the power 5, these 5 actually returns your number of bits, gives you the difference of this. So that's why this is known as the tag value. Actually 5 bits, the lowest number is 50 and the highest number is 51. So in this range, any of the number, tag number is matched with this value. So how to calculate? So that's why in case of direct mapping, the final physical address of your main memory partitioned into these 3 sections. One is tag, second one is block, and third one is word. The size of the memory address is 2 to the power 16. So tag field size is 5. So word size is 4, 2 to the power 4. So rest of the total block in the cache 128, that is the 7 bits. So 5 plus 4 plus 7, so tag value 5, 4 value is the word size and block size is 7. So total 16 bit address, this 16 actually matched with your final total memory size, 2 to the power 16. So this is the value. Now this is the small numerical example. So suppose this type of question actually comes. Main memory size is 512 and cache memory size is suppose 64 and block size is 8. That means each block consists of 8 locations that is transferred at a time. So main memory has how many blocks? So 512 divided by 8, 64 blocks, and cache memory has 64 divided by 8, that is the 8 block. Now we want to transfer block number 5 of main memory to the cache. Then how to transfer? So calculate 5, the percentage of 8, it is returns 5, and 12 percentage of 8, it returns 4. So 5 is the block number of the cache and 12 is the block number returns 4. So this is the block number of the cache. Now this is another type of problems comes with the bit size. Suppose 12 is a particular address of the main memory. So how this 12 this particular location where to transfer? So 12, if we consider our size of the main memory 9 bit, so 12 first converted into equivalent binary with 9 bits. Now word number of the cache is 8. That is the at a time 8 bit 8 location is transferred, so 3 bit. So block value is 3 bit and tag is the total number of main block by divided by total number of cache. So 64 divided by 8 equals to 3 bit. So each sub field is 3 bit. Now you just partition 0 0 0 0 0 1 1 0 0. So this is tag position 0, block position 1, and in the block 100 location is your final value. So if we draw this, suppose this is the cache. So tag value actually placed here. So 0th tag, each tag has block number, total block is 3 bit, total 8 block, suppose B0 to B7. So within the block, each block consists of again 8 bits. So B0 suppose consists of 8 location, memory location. So within B0 was 100 means 4. So that's why 0, 1, 2, 3, 4. That is the fourth location is for your 12. Similarly, if 72 is a particular memory address, you can divide it into according to this data. So 333B, that is the tag number 1, block number 1. Within the block, it is 0th position. Now move to full associative mapping, the second classification of memory cache mapping. So full associative, the definition is any block of main memory can be mapped to any block of the cache. So here some flexibility comes. In the direct mapping, what happens? A particular memory cache line is fixed for a block of memory, but here any block of main memory transferred to any block of the cache. So cache has 128 blocks, 2 to the power 7 blocks, and main memory has 2 to the power 12, 40976 blocks, 2 to the power 12. So any block of the cache contains any of 4096 blocks. So here the block size is not required. So that's why tag value is fixed with the 12. This value is 12, and what size to fix? That is the number of data memory location present in the cache. That is the 4 to the power 4. That is the 16. So tag value is 16. And second one is last one is the set associative mapping. So what is set associative mapping? It is a combination of direct mapping and full. Previous two actually combined. Here direct mapping, the direct mapping technique and the full associative mapping technique. So here one more information we require, that is the set size. So suppose actually set associative mapping declared by name, it is the n-way set associative. So n value is given to you, that is the 4. Suppose I consider here 4-way set associative mapping. So what is meaning? That is 4, this 4 means the 4 cache blocks constitute a set. That is that suppose cache has 16 blocks. So each among these 16, each 4 consists of a set. So if there are 16 blocks, so set number is 16 by 4. 16 divided by 4. That is the 4 set is present. So as per our example, if total number set in the cache is 2 to the power 7, so 4-way set means 2 to the power 2, so 2 to the power 5 equals to 32 set is present in your cache. So any memory location block, now when you decide the set number, so any memory block can be transferred into a particular cache set into the which is defined as in this. So how to calculate? Cache set number actually we define using this formula. It comes from the direct mapping, that is main memory block number percentage modulo of total number of set in cache. So cache set number 0 contain the block number 0, 32, 64, that is after every 32 location it comes. Similarly cache set 1 contains main memory block number 1, 33, 65 in this way. So particular main memory block can occupy any of the available cache block within this particular set. So this part actually comes from again the full way set associative mapping. So this is the combination, that's why it is the combination of direct mapping and full associative mapping. Now for example for the set associative mapping, so main memory block 0 occupy the cache block line, suppose 0, 1, 2, 3 which are present in the cache. So any set in the cache can contain any of the total of 2 to the power 12 divided by 2 to the power 7 blocks of main memory. So this 7 actually gives you the uniquely identify those memory blocks in of the set. So that is why tag value is 7. Here block is not required, that is the block set value is 5. That is comes from here set number, how many set number is declared, and what size to previously fixed, that is the total memory location in a particular block, that is the 2 to the power 4. So total is again 7 plus 5 plus 4, total 16. This 16 comes from your main memory, that is 2 to the power 16, that is the 4096. Now this type of final slide gives you this type of numerical problem actually comes. So some data is given. So from there you just calculate the size of the subfields in the address for the direct mapping, associative and set associative cases scheme. So our target is to calculate for each cases the subfields. Subfields means for direct mapping tag, block and word. Similarly for set associative mapping only tag and word. And finally for full associative set associative mapping tag, set value and the word value. So how many bits required to represent that subfields actually this numerical problem gives. So here these are the data. So 256 MB is the suppose the size of the main memory. 1 MB size is for the cache memory. Total address space is 256 MB. Block size is 128 bytes. That means each block consists of these locations. And for the set associative mappings, 8 blocks in a cache set. That is the 8 blocks present in a particular set. So before calculation, this is the pre-busting of the data. That is the address space 256 MB means 2 to the power 28. Actually MB means 2 to the power 20 and 56 that is 2 to the power 28. So 28 bit address bus. So address size is 28. So that means each mapping, this is the size of the total number of bits 28. Then calculate the main memory contains how many blocks. So main memory size 256 MB divided by the size of the block, that is 128 bytes. So 2 to the power 28 divided by 2 to the power 7, it is 2 to the power 21. So main memory contains 2 to the power 21 blocks. Similar calculation for cache memory contains 1 MB divided by 2 to the power 7 equals to 2 to the power 20 divided by 2 to the power 7 equals to 2 to the power 13. Now how to calculate? First we suppose consider for associative mapping, the second one. So word size is 2 to the power 7, that is 7 bytes. It comes from this 128 bits. So 7 bytes. So tag value is total is 28. So 28 minus 7, that is 21 is the tag value. So this is the 21 and this is the 7. Now for direct mapping is this is the main memory 2 to the power 21 divided by the cache memory, so 2 to the power 8. So that's why 8 bit required for the tag. And block is, what is the block? Block comes from the cache memory, that is the 13 block is present in the cache. And word size to fix for that is 7. So 7, this is block size is 13 and tag value is 8. Total is 28. And finally for set associative mapping, how to calculate the set number of representation of set? 2 to the power 13 is for the cache divided by the block number 2 to the power 3 number of memory location is present. So 2 to the power 13 divided by 2 to the power 3, that is 2 to the power 10. So set value is 10. So what to fix? That is the 7. And finally tag value is main memory 2 to the power 21 divided by the set number 2 to the power 10. This returns 2 to the power 11. So this is the tag value 11. This is also returns you 20, total 28. This 28 actually comes from total address bus, that is the size of the particular address. So this type of numeric problem also comes from this section, cache associative mapping. So now the comparison for all the three mapping techniques, that is this is the concluding portion. That is the direct mapping. These three mapping technique we studied in the previous slide. So direct mapping, what is the easy to implement but low resource utilization. Why low resource utilization? Because if cache memory has some location to store the data from the main memory, but regarding the formula, that is the particular location is fixed for the main memory location. So that's why resource utilization is minimized. Full associative does the reverse. any block can be transferred to any location. So that's why full resource utilization here, but need parallel searching. That is, a searching procedure is used. So that's why which requires complex hardware implementation. And finally, the state associative. This is the combination of direct and full associative mapping. So simple mapping technique as well as this is the better resource utilization. So